Hello everyone, my name is Ivana Dobrilovic and I'm verification engineer at Veriest Solutions. I have over 10 years experience in digital verification. Today I'm going to present you some challenges I encountered in a process of hardware registers verification and solution that originates as a result of working on a different project and verification tasks. First, I'm going to give you a short introduction about hardware registers, their role and types. Then I'm going to speak about read-only registers, their verification and some verification challenges. Afterwards, I'm presenting a solution that covers most of those challenges and that easily could be applied to some other issues. The role of registers in hardware is to be programming interface to the software. They provide static information about design, allow controlling the behavior and features of design, and provide the ability for the software to figure out if design is performing operation as expected or it needs some attention. So hardware is configured, controlled, and monitored through its set of registers. Registers can be classified according to several criteria. Based on their function, they can be broadly divided into three categories: configuration, control, and status registers. There is also division based on type of access. The most common types are read-only, read-write, and write-only registers. Regarding register verification, basic implementation correctness, such as ability to access all registers, check post-reset value, correctness of all access types for different fields, is typically verified by a single dedicated test that exercises only that. The more challenging task is to check functional correctness of registers. For most of the registers, it's spread out across many tests. Those tests are focusing on higher level operation, but while doing that, they use different registers. Hence, also it's not their main purpose, they verify registers indirectly. Read-only registers is a special type of registers that can be only read by software. Those registers are typically used for functions such as status and debug registers, hardware timers, and counters. The status register, as an example of read-only registers, notifies software about various hardware events. Some of them are interrupt status, error status, link operational status, FSM states, etc. Verification of read-only registers is typically tricky. Considering the importance of their function, the goal is to make sure these registers have correct value at any time. The most convenient way to achieve that is to check their value occasionally. There are two aspects of this strategy. First one is related to sequence. So we usually have polling sequence that initiate register read transaction at random moment. Other aspect is the checking itself. This should be done in a common object such as reference module or scoreboard, and actually that is the challenging part that brings more complexity into this verification task. In order to implement a checker for a specific register or register field, we should have an expected register value reliably predicted. For a verification engineer, that is sometimes hard to achieve if we consider duty as a black box as it's supposed to be. There are cases when it's impossible to know the timings of internal events without looking at the internal signals in design. There are several problematic scenarios, and all of them suggest that checkers have to be made more flexible and that there cannot be a single expected value, but rather pool of them. Here I'm going to explain some of problematic scenarios in more details. First, a problem that can be encountered with the counter registers is that their value is changed too fast in relation to the bus transaction cycle, or huge gap between the command and response phase on the register interface could be a problem while reading register at a random moment. For instance, design is implemented to drive back data as soon as it gets request, but the verification test bench gets data only after the response phase is completed and master accepted data. And the bus protocol might allow long response latency, so during that period the expected value might change several times, and we cannot be sure which value corresponds to actual read data. Also, register fields could have different access types, width, and change events, and such fields should be checked independently of each other. For register fields which are 1 bit wide, there is no room for any flexibility in checking since such field can have only one of two correct values. In the example here, we can see how register value changes in relation to read register cycle. It shows how some counter, called counter X in these examples, changes value during the single read cycle. Counter does not even count on every clock cycle, but on some pulse called counter pulse, whose frequency is much lower than the clock frequency. But still, it changes its value 2 times while waiting on read response. First, blue marker points us at the beginning of the transaction when read request is accepted. And counter has 15F hexa value, and it counts down to 15D before response data is accepted, where second blue marker points us. When test bench gets full transaction, accepted value is predicted to 15D hexa, but observed data is 15F hexa, and there will be false mismatch. This example shows similar issue. Here we have one status field, 1 bit wide, as a part of interrupt status register. It changes value during read cycle, while other statuses stay unchanged. And again, there will be false mismatch. So, issue caused by register value change in relation to read transaction should be clear by now. And the most challenging part, race condition between environment and duty. Those two figures show us that we cannot be sure what value will be on read data bus, either first one from the beginning or next one. In first figure, counter X decrements at the beginning of the read cycle, and that allows read operation to catch the actual value of the counter X, that is 24E hexa in this example, and read data is going to match expected data. Hence, we can say it's non-problematic scenario. This figure, on the other hand, represents how easily we can go wrong. Here, counter X decrements 1 clock cycle later, and that results in read operation catching the old data, 1 dB hexa value, and read data is going to mismatch expected data predicted to 1 dA hex. Since it's impossible to exactly predict the expected value and create a relevant, reliable checker, it is the best to add certain flexibility to the checker. The best approach is to determine the necessary and sufficient level of flexibility in the beginning. If we start with the strict checker and later try to introduce a modification, that will make the code less readable and very hard to maintain. This paper suggests a common solution that covers different read-only registers and most of problematic situations in their verification. The solution relies on the fact that the expected value of the register field could be only approximately predicted, and also it takes into account all possible values and their transition order in given time, as it could be of great importance. In the following slides, I'm going to show you code segments that should explain the solution in more details. Status A is a register field whose value is going to be checked. Status A is a register field of the register called reg1 that belongs to block 1, register block. Protocol used to access register is a protocol X, and all checking is done in the common object called model. The solution mechanism requires 3 variables per register or register field declared in the model where checking will be done. First, field that stores an expected value, reg1 status A in this example. Then flag that signals if the register reading is ongoing, reg1 read ongoing, and a queue that will store all expected value while the register reading is ongoing, reg1 status A queue. Idea is to collect all the expected register field values during the read transaction that's targeting the specific register. Once the transaction is done, the checker will verify if the actual register value matches any of expected value from queue. The expected value is calculated based on design functionality. That calculation is represented here by method calculate reg1 status A that is implemented in a model class. Actually, this method runs all the time in a parallel to everything else. Calculation itself is triggered by an event defined in a specification for the specific register field. Once triggered, it calculates the expected value for that register field and afterwards stored in reg1 status A, a variable that is part of our solution mechanism. And that's something we usually do. In addition to that, it also pushes the predicted value to the queue, reg1 status A queue, but only if the reading is ongoing. Registers are accessed using protocol X. Monitor of the agent X reports transaction using TLM analysis port, and our model implements write method as shown on this slide. Basically, once the start of the read operation for the specific register is detected, the flag which says that the read operation is ongoing is set, and the expected value of the register field at that moment is pushed to the queue. This is the first expected value during the read register cycle. For all other potential changes of the register field that might happen until the end of the read operation, pushing to the queue will be done by calculate reg1 status A method as we saw in previous slide. When monitor X reports the end of the transaction, it provides full information about transaction, including read data. Usually, read data will be checked against the single expected data, but the solution here suggests checking if the actual read data or specific data slice matches any element in the queue of the expected values reg1 status A queue. If there is match, the functionality is considered correct. Otherwise, the model issues an error indication as shown here. After checking, a flag that says the read is ongoing is cleared and queue that keeps expected value is deleted. So between two read register operation, expected value is calculated, but nothing is stored in the queue until next read operation starts. The same approach should be taken where there are multiple fields in the register. Here will be one common register read ongoing flag for all fields that belong to same register. Fields can have different trigger events with access policy, and for each field that is going to be checked, here will be declared variable that keeps calculated value and corresponding queue. As we saw in previous example, when register read start phase is reported, it also starts queuing expected values for each field. As those fields can change their values on different trigger events, calculating and predicting their values should be done separately in a model. Hence, we can have calculate reg1 status A, calculate reg1 status B, etc. As shown here, depending on register field's width and position in the register, corresponding read data slices will be checked against expected Q once end of read operation is reported. Flag will be cleared and all queues deleted. There is one thing I want to emphasize here. It's very important to implement a coverage point where only one expected value was in the queue. To prove that exact register field value was checked. Cover group should be implemented to cover size of the reg1 status A queue, distinguishing queue size of 1. Cover group sampling should be done when data is successfully checked and before queue deleting. Why this solution is good? It's good as it's a common solution for one of the most challenging tasks in chip development process. It is good as it starts with a flexible checker instead of exact one, but still satisfies sufficient level of testing criteria. Code becomes more readable and easy to maintain, and it brings ideas that could be easily adopted to other issues. Thank you for your attention.